Hi everyone. So today is our third video on centripetal force, and today we're going to talk about roller coasters. So we've got a roller coaster on your screen with a dip and a crest on the roller coaster, and these dips and crests can be shown in a circular arc to describe the change in motion, right? So for this segment right here, right after this arc right there, then from here to here is basically just free fall, right? Same for here to here. It is just constant acceleration where they're just slowing down until they get up there. But the turn between these 2 points here and here, we can describe as a circular path. Same for the turn from here to about here when they go back into free fall. So we can describe these with circular motion, and we will do that. So let's look at point A and point B. So this video is actually going to talk about 3 ways that you can die in a roller coaster. Not that I don't discourage roller coasters. I think they're amazing, and I love roller coasters. But let's talk about the different ways that this could all go wrong, right? So let's look at point A first. If we look at point A, we have an mg, right, going down, and then we have a normal force going up. Okay. Now, how could this go wrong? Well, it's kind of hard. You can't like launch yourself off of a roller coaster at the bottom of a little valley like that. So let's look at the free body, or the summation of forces, right? Summation of forces along the radius, the centripetal force. You would have n minus mg will equal mac, right? So that means that our normal force will equal mac plus mg. Now, one way for this to go drastically wrong, right, is if that normal force is less than, right, less than your mac plus mg. If the track can't handle that force, right, because it's not strong enough to withstand this, then you are going, the rails would possibly break, and then that is your first way to die, right? So if normal force can't handle the centripetal force, if it can't compensate to continue that circular arc, and mg wins that battle, you fall through the roller coaster, right? That's always a bummer. Now, the next one, if we look at point B is a little different, right? Because we have here, we have a normal force and we have an mg going in the same direction. But on a roller coaster, you don't actually want that normal force, right? So when we look at a roller coaster, right, think about all the times you guys have been on roller coasters. If you haven't, imagine. But when you go over the crest of a roller coaster, you actually kind of get lifted up out of your seat, right? And then you've got those arm bars or the lap bar that kind of keeps you in the chair. So that moment when you're going over the crest and you feel that little bit of weightlessness, you actually get lifted out of your seat. If you're not touching your seat, now there's no more normal force, right? So that means that we just have pure mg going in that direction, which is the goal, right? That's kind of what a roller coaster wants you to feel. So if we have mg equals mac, then that is the desired effect. However, what if your mg can't handle that, right? So if your mg is actually less than the acceleration needed to fulfill that arc, then you're actually not going to stay in that arc. You're actually going to get launched, right? So if there is no lap bar, or if there is no shoulder bars, you just continue to sail right on through, right? So this would be the second way to die on a roller coaster if your MG isn't enough. Now, modern engineering obviously has fixed that problem with the shoulder bars and the lap bar, but they still need to consider these forces, right? Now, let's actually look at what happens when we have mg equal to mac, right? Now, if we have mg is greater than mac, it's kind of a lame roller coaster, right? If you're going over the crest of a roller coaster and you're just sitting firmly in that chair, that's kind of a bummer, right? So we do not want that to happen. But ideally, you have your mg just equal to mac, so you don't get launched off the coaster, but you also feel that little bit of weightlessness right there, right? So the m's here would cancel. We could say that g equals ac, which could equal v squared over r. So now looking at this equation, we can actually find what is the speed limit, right? If we go any faster, if we go faster over here, if AC is greater than G, no go. And then we just showed up here, if AC is less than G, again, no go. That's kind of lame. So if we multiply that R over, we get GR under a square root to equal V. This is essentially the speed limit, right? This is the fastest you can go without being launched. And you also want to hug that speed limit as much as you can to make the roller coaster as fun as possible, right? So we'll use that in a future problem. But here are these two possible ways to die. We'll go over a third way to die later. But one way to die is to get launched off the coaster on a crest, or if you come over here, if you go down to a valley, the rails may fail, right? So those are two possible ways to die in a coaster. Now, roller coasters number 2. What we're going to do is we're going to calculate some forces and speeds. So part A, calculate the force on the track if the car has a speed of 20 meters per second at point A. So we're focusing on that dip, that valley. And then we have the mass of 500 kilograms and a radius of 10 meters on that circular turn there. So let's look at this. Let's get a free body diagram, shall we? We've got normal, and we've got mg. So if we want to look at the centripetal force, right, that's what we're calculating. It asked calculate the force on the track. Oh, wait, it asked for the force on the track. Now we need to think about this. What would be the force on the track? Well, we would need to think about Newton's third law here, right? So the track is exerting a force on the car, keeping it in its path, right? That would be our normal force. Now, if we want to know what is the force the track is feeling as the car moves, that would again be the normal force, right? Equal but opposite reactions in that. So we want to solve for the normal force on this problem. So again, we will still set that up. Summation of forces for centripetal force. We have N minus mg is going to equal mv squared over r. And we have a set of givens. Let's get our givens real quick before I continue on. Our speed is 20 meters per second. Radius is 10 meters. Mass is 500 kilograms. I believe that is everything. Yes, okay. All right, so if we want to solve for normal force, right? Normal force is going to equal mv squared over r plus mg. We factor out that m to get v squared over r plus g. We have all those variables. Let's plug them in. We've got a mass of 500 times this velocity of 20, square it, divide it by the 10 meter radius plus 9.81. So if we do that math, we get 24,905 newtons, right? Yep. Yep. Okay. 24,905 newtons. So like we talked about in the last slide, the track needs to be able to withstand this force it feels as the car goes by. So it's got to withstand 25,000 newtons of force if the car has a mass of 500 kilograms. So that's a lot of force that this structure needs to hold up. All right. Now for part B, calculate the maximum speed the vehicle can have at point B to remain on the track. And now we've got a wider turn up there. You can see on that circle diagram there, it's a wider turn. We're going to assume a larger radius of 15 meters instead of 10. So we actually have this equation, square root of GR, but let's go ahead and show how we got that again real quick. We've got mg. We have no normal force on that crest if we're doing it right. So mg equals mb squared over r. The m's will cancel out. So then we have g equals v squared over r, and gr under a square root equals b, right? So if we want the speed limit, let's take the square root of 9.81 times, this time it's 15 meters. It's a little bit wider of a turn. So then we get a velocity of 12.13 meters per second. So that is the maximum speed you could go on this circular arc of a 15-meter radius if you wanted to stay on the track, as long as that is a circular arc. Okay. All right, so we are able to apply both of those ways to die, right? It needs to withstand about 25,000 newtons, and you can only go 12.13 meters per second without your car starting to leave the track. But again, modern engineering has that clamped down pretty good. All right, roller coasters 3. Now we're going to talk about the teardrop. Okay, so the teardrop, we've got this coaster in Six Flags in Illinois, incorporates a teardrop loop in the track. This is also called a clothoid loop, if you want to look up what a clothoid loop is. The biggest loop is 40 meters high with a maximum speed of 31 meters per second, nearly 7 miles per hour at the bottom as you're coming out of it, I believe. Now calculate the radius of the top of the arc in the teardrop if the riders feel 2G, quote unquote 2G of centripetal force at a speed of 13 meters per second. So first, let me draw this real quick so we have a better understanding. So a clothoid loop. Clothoid loops are kind of hard to draw, but a clothoid loop has this path right here, right? You go up here, but then you take a dip right there and continue your path. Now, this section here has its own circle that we can analyze with its own radius right here. There it has a radius r. These circles also have their own radius r going out as well. So this is a clothoid loop, very similar to a teardrop, right, that we're using here. So this has a height of 40 meters in the clothoid loop in this teardrop. It's got a maximum speed of 31 meters per second. Now, we want to calculate the radius at the top of the arc. So we are talking about this little r in the green circle. What is the radius of the top of the arc in the teardrop if the riders feel, quote unquote, 2G of centripetal force at a speed of 13 meters per second? So we've got FC is quote unquote 2G. We'll talk about that in a second. The velocity is 13 meters per second, and the radius is what we're looking for. Now, when we talk about 2G, right, centripetal force, that's kind of a relative term, because when you look at what that means, that really means you have MAC, but AC is the real 2G, right? G is acceleration, not force. So depending on your mass, right? Depending on your mass, everyone's 2G will actually look a little different force-wise. But acceleration-wise, everyone experiences 2Gs of centripetal force when your acceleration is 2 times 9.81 meters per second squared. And that would be 19.62 meters per second squared. We have acceleration, we have v, we want r. So we can actually skip the centripetal force part, just go straight to AC equals v squared over r. R would equal v squared over AC. So there we have 13 squared divided by 19.62. And you get 8.61 meters. So that is the radius at the top of this clothoid loop. Right there in that green circle, the radius would be 8.61, but the height overall is 40 meters. All right, so that is the radius of the top of the arc. Now we've got a couple problems coming up to continue this. So teardrop continued. Suppose a circular loop of radius 20 meters. Okay, so we've got circular loop. That's not very good, right? Let's just draw a circle. There we go. A little bit easier to do that. So we've got radius right there of 20 meters, reaches a height of 40 meters. Calculate the centripetal acceleration at the top if the velocity is again 13 meters per second. So we have v is 13 meters per second. We have r equals 20 meters. We want AC, which is v squared over r. So we would get 13 squared divided by 20, and you get 8.45 meters per second squared. Now, it's a bit concerning. Why is the answer to B an issue? What would the coaster have to do if you did not use a teardrop to make this turn? So if we're using a circular loop, well, first we see that AC is actually less than G. So the acceleration to make this turn is actually weaker than gravity. But you can't escape gravity, right? So this is going to cause us an issue here. That means that we are going to have G affecting us. So let's look at this real quick. Let's analyze the normal force in this scenario. So at the top, right? If we in a loop-de-loop, you've got normal force and you've got mg, right? Now on a crest, remember we try to avoid normal force if we're going to make our roller coaster right. But in a loop-de-loop, right, normal force is going to keep you in the circle. So we've got normal force plus mg. That's going to be our FC, and that will equal MAC. So if we calculate our normal force, we get m times AC minus G, which regardless of your m, that's going to cause an issue, because if we have 8.45 minus 9.81, we're going to have 1.36 meters per second squared. That means that you're going to accelerate downward. Gravity is actually going to win, and it's going to pull you out of your seat. So if your normal force starts ending up being negative, that doesn't mean that your normal force, your chair is now pushing you out of the loop. That means the math didn't work. And that means that you are now going to fall out of your seat in the middle of this loop. This is your third way to die. So that's something we need to be careful about. And that's also why we have the idea of the teardrop loop, right? We've got the clothoid loop that actually allows for higher loops, right? Where you go all the way up to 40 meters, and it also gives you a tighter turn. You also get a higher centripetal acceleration, right? You get a centripetal acceleration here of 19.62. You're going to feel 2 G's on that one, which is exciting. Up here, you're not going to feel any G's from the turn. You're actually going to fall out of your seat. All right, so that's what we have for roller coasters. We're going to continue chapter 6 by doing some calculus as we go forward. We're going to start integrals next.